Starting. All right, so this is UM GEO 420 Hydrogeology, April 16th lecture. And I'm going to share my screen. Let's go over some stuff with the exam that we just handed back. All right. So I should be sharing my screen, and I'm going to pull the key up here so we can look at it. Everybody did pretty well on this first sketch. Just remember that capillary pressure becomes negative as we go down from porosity to the volumetric saturation, or sorry, to the residual saturation. Everyone did pretty well on that one. Relative hydraulic conductivity was one where I got quite a bit of different answers. And a lot of people had a curve that, let me see if I can open up my, what was that application? That drawing application. I don't know, can't find it. Anyways, a lot of people had a curve that that looked kind of curved the other way and was asymptotic to porosity and basically exponentially increasing. All right, the maximum relative hydraulic conductivity can get to is 1. All right, so it's going to go up, it's going to hit 1, and it's going to stay at 1 after porosity. All right, so the curve can't go like this. That implies that relative hydraulic conductivity exponentially increases as we approach porosity or full saturation. So it's got to flatten off and be asymptotic to 1. Another thing that got people a fair amount was that for an unconfined aquifer, the aquifer equation is Kx times H. We have this extra H in here. I also took if you said that Kx times H is equal to the transmissivity, that was a valid answer. But important thing is Kx times H here. And then a lot of people were using SS. So the specific storage, that's the principal difference between an unconfined and a confined aquifer. This S is SY plus SS times B. For variably saturated flow, you needed to use Richard's equation. And so a lot of people were just throwing up the regular vertical confined aquifer equation, right? You need to have the relative conductivity term here. And then your storage here is now a complicated term that accounts for the change in saturation per change in head, that's the CM, plus the saturation times the specific storage. Okay, the next thing, people did pretty good on this stuff. Everyone did well, pretty much on this equation, on this problem. On problem 6. The point here was to calculate the groundwater divide location and see on what side of the groundwater divide our spill was. So it actually didn't matter whether you used the drawing numbers or the numbers in the text. The water table divide was past the spill location, And so the flow would go to the Bitterroot River. And here's the groundwater divide equation. All right, on 7, flow nets for the most part were okay. Some people got really crazy with no squares. And I took some points off if you just were completely off on no squares. I'm not expecting perfect squares, but I had several flow nets where it was very, very not square. All right. To calculate flow through this aquifer, you should have used the flow net equation, this guy here. And one of the things I wanted to do is to talk about how we calculate the head contours or the number of head drops. Because almost no one counted the number of head drops right. So you start, so here's the point. My first head drop, all right, this guy right here, we start at 0. So this is 0, 1, 2, 3, 4, 5, 6 head drops. All right, you can think about it this way. My first head drop is this first contour. So everyone counted the number of contours. Well, not everyone, but a lot of people. It is the number of head drops. So you start at 0, 1, 2, 3, 4, 5, 6. You can check that this is right because if I divide 0.4 by 7, and then I add this to each one of these increments, I'm not going to get to 10.4. If I divide 0.4 by 6, I will get to 10.4 by the time I get down here. So this should be 6 down here. I took a whole bunch of different ways you could have calculated this discharge. I do it for a single stream tube. You could do it for approximating the area for the full aquifer. You need to use the correct area and you need to use the scale basically. So this gives you some spatial scale here. You could have calculated the total cross-sectional area of the aquifer. The other thing that a lot of people were doing was just taking 0.4 and 1 kilometer. Well, you've got a flow net here and you can see that your head difference is not the full 0.4. And your flow net allows you to calculate exactly what, or very close to what your head would be at each one of these locations. So you could be more accurate than just a 0.4 meter head drop between these 2 points. But the basic thing I wanted to do is calculate the Darcy flux, little q. You could do it a variety of ways. Then use V is equal to Q over N. And then finally, the time is equal to the distance over the velocity. Should have got an age on the order of 100 years or so. All right. Problem 8. Well, so the first thing I ask you to do here is to calculate the pressure head or the capillary pressure just below the tailings pile, giving you that the first of all, the unsaturated porosities, or sorry, the unsaturated zone properties. All right. And then that the sand beneath the tailings pile is has a volumetric water content that is constant at 20%. All right. So the capillary pressure here, we're going to calculate using this 20% volumetric water saturation. So you needed to do two things. The first was to solve for the effective saturation. All right. Using the properties here. So theta sub r was equal to 0, and this just became the volumetric water content, 0.2 over the porosity, 0.375. You could get SE, and then you needed to solve the Brooks-Corey relationship for SE. You needed just to rearrange and solve for the capillary pressure. So when you do that, you get a capillary pressure or a pressure head just beneath the tailings pile of negative 0.315 meters. All right, the next thing I wanted you to do was calculate the relative conductivity at this pressure head. So we use the Brooks-Corey equation for the capillary pressure, or sorry, relative hydraulic conductivity, plug it in, and your relative hydraulic conductivity should be on the order of 0.03. All right, then the final, or part C, was calculate the travel time from the landfill to the water table. So you needed to do two things. The Darcy flux in the unsaturated zone would be the relative conductivity times the saturated hydraulic conductivity times the head gradient in the Z direction. So this was the first move. And the trick was getting the head gradient in the Z direction. You could do any datum. I chose the water table as the datum, which meant that so if you choose a water table at the datum, the head at the water table is equal to 0. And the head up here is equal to the elevation, 10 meters, plus the pressure head, which is negative 0.135 meters. All right, so this head up here is like 9.7 meters, roughly. The head down here is 0. The head gradient is 9.7 meters over 10 meters, should be something like 0.97 meters. Or sorry, 0.97 meters per meter. All right. Once you have that, it's Q is equal to KR, 0.03 times the saturated hydraulic conductivity times my head gradient, something like 4 times 10 to the minus 7 meters per second. Now, one of the tricks here is that the velocity in the unsaturated zone is equal to the Darcy flux divided by the volumetric water saturation, because the area which the water can flow when you're unsaturated isn't the full porosity, it's the water, it's the porosity that's filled with water. All right, so I didn't take a lot of points off, but this is a thing in the unsaturated zone that the velocity you divide by the volumetric water content, not the porosity. And then our classic, the travel time is equal to the distance divided by the velocity. Okay, so when you do that, you ought to get a travel time on the order of 50 days. All right, calculate the discharge per unit width. So I wanted you to calculate the discharge along in the direction towards the well, and I per unit width, I tried to give you an explanation of what that meant in and out of the page. This was clearly unclear to a couple people in the class, but the bottom line is you could calculate a head gradient here, and you can just use Darcy's law. It's a real simple application of Darcy's law the main thing I was looking for here is that you could figure out which directions you would calculate the head gradient. So I wanted you to calculate a vertical head gradient for this travel time, and I wanted you to calculate the horizontal head gradient for this travel time and use the correct form of Darcy's law. So if we do this, the correct form of Darcy's law, the discharge per unit width is Q over W is equal to K times B over DH dx. The thickness B is a trick because it's 30 meters here and it's 29.9 meters here. So what is the discharge? I accepted either 30 meters or 29.9. Probably the best number here to use would be to average them. That's what I did, but I accepted anything that was reasonable. And then the head gradient is 30 minus 29.9 over 150 meters. Right? So just the head here minus the head here divided by the distance between those two. All right, you should end up with something like 2.6 times 10 to the minus 7 meters cubed per meter per second. Okay, so just some rough numbers. So the average, the class average on the test was 85%. It's reasonably high for one of my groundwater tests. So you guys did pretty good. High score was like 97%. So, you know, people did well. And the main things that I wanted to hit where I saw a lot of error was how do we count the number of head contours here? That was something that most people didn't do right. And then you know, some people just didn't. I got a lot of different answers for how you calculate the pressure head right here, and the trick is to use the volumetric water content and calculate the capillary pressure at that point. All right, so any questions about the test? Okay, if you have questions later, let me know, email me. I'm assuming, so the way I'm grading these is I'm annotating the PDF via Moodle. Are you guys able to see all those annotations? Yeah? Okay. So if you need explanation or if something's unclear to you or you feel like I was too mean or too nice, you know, feel free to discuss it with me. And we can talk about where you went wrong and what I was thinking when I graded. Okay, so if I don't get any more questions about the test, and I'm going to move on and start lecturing, if that's all right. Okay. All right, so when we left on Tuesday, we were talking about this problem where we've got this old paper mill south of Missoula along the Clark Fork, sorry, west of Missoula on the Clark Fork. And we're interested in whether any contamination from the wastewater treatment system of that paper mill could be moving towards the river. All right, and so we first opened up this subject in terms of thinking about groundwater, streamwater interactions. But a lot of what you guys said was that in order to understand whether the contamination would move from our plant to the river, we needed to drill wells and understand what the water table configuration and lithology was between the river and the mill. So today what we're going to start doing is talking about drilling and in general aquifer characterization. All right. So the things we would need in order to figure out sort of how fast water was moving from our mill to our river, well, we need the head gradient. So we need DH, DL, but we also need hydraulic conductivity. We're going to want to know something about porosity. We probably need to know something about our aquifer architecture. So what's the depth, B? So these are all the kinds of properties of the aquifer that we're looking for when we start a aquifer characterization program. So let's start talking about aquifer characterization and how we go about it. So let's start a new section here. All right, so congratulations, your guys' consulting firms won this project. And so now it's time to start thinking about how are we going to actually understand where and when groundwater and how much groundwater is coming from the plant to the Clark Fork. So by the way, this problem is super germane. It's happening right now. So there was this paper mill just outside of Missoula. It has been shuttered for over a decade now. There is some indication, people have sampled in the river, and there is some indication that there could be some contamination. We know the groundwater around there is very contaminated. And the EPA right now is in charge of figuring out what is the potential for contamination at this site and how would we go about a remediation. And so all this is happening right now. The players are the people who own the property, right? They don't want there to be a lot of contamination. It's unclear how liable they are because they bought it from the company who produced all the contamination. So it's unclear whether the corporation that owns the property now is liable for the previous contamination. And this is a really common thing in America. You have a company, you do a lot of industry, and then when you're done, you sell the property and the company, and your legacy of contamination remains. So the people who end up having to deal with that are the taxpayer via the Environmental Protection Agency, right? So the EPA is now in charge of deciding how bad the contamination is and what the remediation plan is going to be. And the site characterization and the contamination characterization and the development of the conceptual model of the site is happening right now. All right, so the EPA is doing everything that the EPA, and largely through local consulting firms who do the bulk of the technical work, are going to be doing all the things that you guys are doing here at the end of the class. So figuring out how we do the aquifer characterization, how do we build our conceptual model, and how do we understand how this system works so that we can design a remediation plan. Okay, so your consulting firm, the EPA, comes to you and says, look, we need to know what the alluvial groundwater system near the Clark Fork, between the mill and the Clark Fork, what does it look like? What kind of aquifer do we have? What are the head gradients? What are the general dynamics of the flow? We need to understand what this aquifer looks like. And this process is part of a much bigger process that's conceptual model building, right? And so when we build a conceptual model of the site, the idea is that we're going to end up with some cartoon drawing that gives us all the ingredients of the boundary value problem, so that we can go on and think about how we would model it, how we would calculate flow path times, discharge volumes, all this other stuff. What we need to do first is understand what the aquifer looks like. So there's three, well, I'm not going to say three. There's a few basic steps that we do when we start off an investigation. And the very first thing we do is a desktop study. So we start with the desktop study. All right, and here the idea is to go out and research and understand who's worked in this area. Who's done what in the area. Mark is asking me to make the font bigger. Okay, so who's done work in the area? What's the basic geology and hydrogeology of the area? All right, so this is largely what you're doing in your final project. You're doing your first desktop study. You go out and you figure out who's studied the groundwater system in this area. All right, so as an example, I've done a bit of a desktop study for this area, and we've got two or three master's theses looking at the hydrogeology, not right here, but of the sort of 9-mile area of the Clark Fork Valley. All right, so those are the kind of data sets you're going to be looking at. Who has gone in and summarized drilling cores, thought about the geologic history and the setting, and what the depositional environment was. And so these desktop studies allow you to start figuring out what is known about the area and start forming your initial thoughts about this zone. So things I know about this Clark Fork area, well, we're in the western Montana zone where we've got sort of mountain blocks on either side. We've got this alluvial valley with the river in it. All right, so we've got mountain blocks, and we've got an alluvial aquifer here. And we know that in general, these alluvial aquifers are pretty well connected to our river system. We know that the top 100 meters or 100 feet or so of this alluvial aquifer is sort of glacial deposits. And we know that some of them are lacustrine, so they're part of Glacial Lake, Missoula. And some are fluvial or river deposits. And some are flood deposits from Glacial Lake, Missoula flooding. So we have this mix in here of really fine clay layers from the lacustrine. We've got sands and gravels from the fluvial and the flood deposits. All right, so these areas here are going to be heterogeneous. We're going to have very high permeability sands and gravels, and we're going to have clays, fine-grained clays and silts left over from the lake. And then beneath this 100 meters of glacial material, we have clay-rich, fine-grained sediments of the Renova Formation. All right. And most of our groundwater flow is in this upper 100 meters. And most of our connection to the river is in this upper 100 meters. Okay, so this is information that I've gleaned, A, from just knowing the general geology of the area, and B, from reading a few theses, all right? Master students who worked in the area. Hasn't been a whole lot of other work published. And so the job now is going to be coming in here and thinking about what my connection, what does my water table shape look like? Am I dominated by these clay deposits? So I have a really low permeability zones. Am I dominated by these gravel deposits or these, or is it really mixed or is it homogeneous? Okay, so this is our, our basic study. And this is, we don't have to go out in the field. We're just looking at stuff that's been done already. Okay, so step 2 is often thinking about how do we characterize this thing with broad strokes. So what kind of field work could we do that gives us a broad picture of what's happening? The other really important thing that we get from a desktop study is what are the wells, what are the existing wells in the area? All right, so common sources are, this is the USGS National Water Information Center, NWIS. And if you're in Montana, it is the Montana Bureau of Mines and Geology. They have the GWIC, Groundwater Information Center, all right? These two sources have databases of all the wells that have been drilled in the area. Now, by law, if you drill a well in Montana, you need to file its location and a driller's log that we're going to look at here in a bit, and understand with GWIC, so that every well drilled in the state, its drilling, its completion, and its all the information we can get from the drilling is posted in this database. So that's really great source for us to start looking at where other people have drilled in order to build out our conceptual model. All right, the other thing we can do to start building out a rough idea, I'd say the next step of site investigation would be broad characterization via things like geophysics. All right, so it could be that I really want to try and map out all these sand lenses or understand where they are or how frequent they are. I may want to try and look at the boundary between the gravels and the silts here. I might just be interested in how deep the sediments are. These are all sort of basic questions that I can try to constrain with geophysics. So seismic surveys, ground penetrating radar, electrical resistivity, microgravity. All right, these are all techniques where you need to take a whole course to understand them, but they are what we call non-invasive. So we basically just lay some instrumentation out at the surface and we're able to get some characterization of the subsurface. Now, another term for geophysics is geofantasy. And that is because there's a lot of, I'll say, there's a lot of ways you can interpret the data. So you need ground truth. All right, so geophysics is wonderful. I have a PhD in it, but I'll say that until you start drilling, you don't really know what's happening. And so that brings us to our sort of fine detail characterization. And that is drilling All right, so here's the reason why you do all these other things before you drill. So you can pretty much count on a water well. You know, here we don't have to go very deep and we're not very far away from a reasonably sized urban center. So you're probably looking at $100,000 to $200,000 a pop per well. All right, so you don't just drill without thinking about where it's going to be and what exactly you need that hole and that well to do for you. All right, so we really need to be smart about where and how many wells we're going to drill. And we do that by building this conceptual model first. So doing the desktop study, doing geophysical characterization, and figuring out where exactly we need more information and we need to know exactly what's going on. So the first thing we're going to talk about, or what we're going to talk about next, is means of drilling and ways of drilling. So I'm not sure if this is going to work, but I'm going to try and show videos on my machine that then have to go through Zoom. So I don't know whether the internet's going to work. If not, I will post a PDF and you guys can click on the videos yourselves. But let's just look at some of these drilling techniques. All right, so the bottom line is we need a hole in the ground. And there's several methods to do that. And I'm not going to cover all of these methods. I'm just going to cover the basic classes or types of drilling. The first one is called wireline drilling. And let's see if we can get this to play and whether or not it'll show up on Zoom for you guys.
The percussion method of drilling, cable tool.
Wait, first of all, can you guys see that and hear that? Yeah?
Yeah.
Yeah.
Okay.
Yeah, that's
is one of the oldest cutting actions utilized in the drilling industry. Developed in China over 4,000 years ago, the cable tool is tried and true, responsible for millions of successful wells around the world. This system is still used today because of its own unique advantages, which include one-person operation, low equipment cost compared to other systems, simple, rugged design requiring minimal maintenance, low horsepower requirements of this rig, and finally, cable tools have proven to be virtually indestructible. These machines are mainly used today for drilling in unconsolidated materials and soft rock formations where relatively shallow depth wells are required, approximately 100 feet or less.
Okay, so I want to stop here real quick. One of the things that he said that's really important here, he said sort of what materials this drilling method is useful for, right? So soft rock and not real deep. So one of the first things that we do when we think about how we're going to put a well in is we think about, well, what kind of rock are we in? How deep do we need to go? And that'll let us know like what kinds of drilling techniques we need to do or use. So as an example, we don't need to go very deep and we're in unconsolidated sediment. So wireline could be a potential possibility here, all right, for us. So we'll talk a bit more about, you know, application, but one of the important things to think about is where we can do these types of methods.
Penetration rates are characteristic of this drilling system. Support equipment required for this drilling process are basic: a small truck with welding equipment, torches, and a small amount of makeup water. A separately mounted deck engine powers the rig. The cable tool uses the percussion cutting action, utilizing a 1,200-pound drill string. And
okay, so here's a picture of a hammer tool drill bit. All right, and it is just a piece of really heavy metal, and then these little indentations you can see here are diamond cutters. All right, they're pieces of really hard carbide steel with diamonds in them. All right, and so basically all that happens is this thing goes up and down and slams the rock and just smashes it into bits.
a carbide button bit. This bit goes up and down once per second, performing 4 important drilling functions at once: penetrating the material beneath the bit, reaming the sides of the hole, crushing the geology into fine particles, and mixing these cuttings with water. The drilling action, in conjunction with approximately 5 gallons of introduced water, mixes with the cuttings, which require bailing after approximately 4 feet of drilling. This flushing system requires the drill string to be tripped out of the hole and the bailer to be tripped into the hole.
Okay, so two things. Some drillers talk and vocabulary. So tripping in and out of the hole is getting your drill stem down into the hole to the bottom of the hole or pulling it back out. All right, so that's tripping in and out. One of the big things with drilling is that we got to get the cuttings or the core back to the surface, because as we're drilling, we're crushing rock up. We need to get all that stuff back out, right? Those cuttings for the geologist are our best source of information, all right? That's where we're going to see what kind of lithology we're in. Now, with the wire line, because we're drilling by pulverizing, the cuttings are really hard to interpret. They're basically ultra smashed up bits of rock. So that's another thing with all drilling methods, is what we think about is what is the recovery of the rock. So wireline is the cheapest, the slowest, and it just destroys the rock. So it's got some advantages, but one of the, we don't get any kind of real rock back to the surface, and you'll see that here in a sec.
The bailer is simply a hollow tube with a check valve on the bottom, which fills with the cutting slurry mixture. The action of the dart valve enables the bailer to collect cuttings for ID and recording purposes, as per Regulation 903, as well as removing accumulating cuttings by dumping them in the mud spout.
Okay, so this is drilling mud, all right? And drilling, let me put it this way, in big time drilling operations, like if you're in the oil patch, they have drilling mud engineers, all right? They have people who design mud. But this is what it basically looks like. It's a slurry, all right? And here they're saying, hey, you can ID the rock from this. All right. Okay. Maybe the color, the mineralogy, potentially, if you take it back to a lab and do some analyses. But I don't know whether that's a shale or a granite or whatever. I mean, it could be many different things. I know that it's like, light brown and looks very fine grained.
Bailer is also useful for measuring approximate water pumping rates and levels at any time during the well construction. The cuttings from the borehole are usually well mixed and small in size, representing an accumulation of the formations encountered since last bail. Cable tool drillers have developed the ability to interpret the feel of the drill string to improve well log accuracy and in identifying aquifers. The cable tool drilling process typically consists of drilling, removing the cuttings, identifying the geology, monitoring the water flow if present, and then advancing the casing. There are 2 methods for casing advancement.
Okay, so I think we talked about this earlier, but very beginning of the class, but it might be worth revisiting here. Some of this terminology. So, well construction basics. Okay, so let's, here's our land surface. And, we run our wire line here or whatever method. And what we end up with is an open hole. All right, that is vertical down into the subsurface. All right, this open hole, first of all, is, you know, only supported by the soil and the rock. So when I'm in loose, unconsolidated rock, like where we would be drilling for Milltown, it's probably going to collapse. All right, it's not going to stay open. So we got our open borehole here that, you know, is going through different rock types. And we might be soil up high, then we get to bigger gravels, and then we might get down into a bedrock or something. All right, this is a typical sort of profile. All right, so we've drilled this hole. If we just leave it open, these unconsolidated gravels and sands, they're going to collapse into the hole and we'll lose our hole. So what we do is we drive casing down the hole. All right, so there's two things. This hole will be the hole will be irregular, and depending upon the drilling method, it can be very irregular. So these wireline holes, because you're just taking this bit and just pounding away, they go everywhere. They're really rough, and they are not very smooth at all. They can be very wide in some places and very narrow in others. All right, so it's not a perfect cylinder. We drive casing down, which, despite my imperfect lines, is a perfect cylinder. All right, so casing is just a metal or plastic pipe. All right, in most cases today, we're going to do PVC because it's cheap and it doesn't, it's not affected by water. It doesn't rust. All right, but a lot of old wells are cast iron casing. All right, and all this is, the casing is just pipe. Is solid, is you know, unperforated pipe. And its mission here is to keep our drill hole open. All right, so in this case, we might drive some amount of casing through our unconsolidated rock and down into our bedrock, as an example. And then once we're in the bedrock, the hole might stay open, all right? Or we may want, the bedrock may be the zone where we really want to pump groundwater out of. Maybe we're interested in, you know, some fracture zones here. We want to understand water in these fracture zones. All right, so we can use casing and we can nest casing. So a lot of times we'll have what we call an outer casing that we drive through, say, the upper unconsolidated portion. And then we'll take another pipe that we run down inside the outer casing. And this one, we screen. And remember, we looked at borehole screen at the beginning of class, but it's basically, so this is my screen. And this is our slotted pipe. all right? And it is an interval of slotted pipe, and it allows water to come in through those slots, all right? So that our water inside our pipe here is coming in only from our screened section. All right, so we've got casing. So here we've got outer casing, we've got an inner casing. And we call this inner piece casing if it's intact pipe, and then where it's perforated, we call screen. All right, so here our screened interval would be over this fractured zone, and we'd be cased everywhere else. Now, super important point here. If I only want to get water out of the screened section, I've got to seal the hole everywhere else between the casing and the hole. Does that make sense? Otherwise, water could come in here and come up through here, or water, say in this portion of the material, could come down, work its way down the annulus and into our screen. So this area between the casing and the soil is called the annulus, and we have to seal the annulus. All right, and we do that with basically two materials get used: grout or cement, or bentonite. And bentonite is this magical stuff we use in drilling. It's a swelling clay. And it swells when it comes in contact with water. And it has really low conductivity. All right, so one way or another, we've got to seal this annulus. With grout or with bentonite. And if we want no water, if we want all our water to come into our pipe here, we're going to have to seal this annulus too. Okay, how do you think we get cement into this zone here? It's got this little,
pour it.
You just pour it right here up the top and hope to God it just comes down through all these little cracks.
I mean, they have like long tubes that you could probably
Okay,
push
so
down.
Good point. So another driller's, more driller's vocab, this long tube that we might say put down our annulus and pump grout or bentonite out of, it's called a tremie tube. All right. And a tremie tube is both a verb and a noun. So if we might say something like, yeah, we'll tremie the hole from 10 to 15 meters or something like that. That means we're going to run a tube down and try and tremie the annulus, or pour concrete in the annulus. There's other methods to fill this, and one is to stop drilling. So to drill, say, down to drill down to our bedrock interface, fill this entire well hole with grout or cement, and then let that set overnight, and then re-drill and put our fill the entire hole with cement, put our casing in there and let the whole thing set in, and then we re-drill out our casing. So you'll see some of that here in a sec. All right, so main things I wanted to do here is just talk about the vocab. Casing is this unperforated pipe, and one of the things that's an art is figuring out how do you get your casing down before your hole collapses. All right, and then we got to figure out how to seal it. All right, and then we're going to screen over intervals of interest. All right, so if we're trying to drill a well to produce water, we would screen over highly productive zones. If we're scientists and we're interested in a certain part of the aquifer, we screen over that aquifer. All right, so one of the things, if you're in unconsolidated sediments, you drill down. If you trip your drill stem back out, you can have a lot of collapse as soon as you pull your drill stem out, right? So if you're in unconsolidated sediments, you gotta figure out a way to advance your casing before you trip out.
Could you put it as like an outer? So you have your drill, and then you slide it. The casing is a sleeve. So as you drill down, you slide the casing down. You drill some more. You slide it down.
Yes, you can do that. There's a couple problems. Your casing has to be wider than your drill bit then.
Yes.
And so that is a problem. That's hard. Because your drill bit sets the size of your hole. Right?
Yes.
We still do it. But you've got to drive that. You end up having to drive casing and shave off parts of the hole, basically. So you can't just slide it down. You gotta, bang it down. And then you got a whole lot of operations happening up here. We do it. It's hard. Another way is to have you can drive as you go. You can also have your casing fit inside your drill stem. And then you pull your drill stem up around your casing and the hole collapses in around your drill stem. That's probably the easiest and best way to do it. But there's lots of methods. We'll get into some of those.
So your casing would be smaller than your drill?
Yeah, your casing would be smaller than the ID of your drill bit. We'll talk about it here. It'll make more sense in a bit.
And the drive blocks.
Okay.
The drive cap is primarily used by cable tool operators until such time as increased friction is encountered.
So here he's driving the casing down the hole.
Then enable more energy to be transferred to assist with driving the casing down. The casing advancement continues in overburdened situations until such time as a suitable aquifer is encountered, or until the casing is firmly seated in bedrock, after which casing is no longer required, as the geology itself, or rock, stabilizes the hole. The large bowl reel shown here supports the cable, which in turn supports the drill string. The speed at which it is turning here is typical of hole advancement in unconsolidated material. Ideally, casing is added in 10-foot sections to improve efficiency. Additional casing sections are usually welded, ensuring a watertight seal, as required per Regulation 903. The angular space between the working casing and the permanent casing is commonly grouted after borehole construction.
All right, so angular space between the working and the inner casing is grouted after construction. All right, so all that terminology should make some sense now. Okay, so that's wireline. All right, so wireline is cheap, it's slow as hell, but it's easy, and we still do use it for sure. But it's not the most modern method of drilling. So more modern, another method that we use, and we use a lot at UM because I have one of these, is a geoprobe. And it's another method that's good for unconsolidated material. All right. And it's another like pounding or mechanical advancement. So let's check out a geoprobe. So the geoprobe, I'm just going to say, is the workhorse of environmental and geotechnical subsurface geology. Anywhere where you're in unconsolidated sediments, it's really the main drilling technique used, and you'll see why here in a sec. Okay, so this is the geoprobe. This one's track mounted. It's sweet. I wish I had one like this. And this is called the hammer. All right. And this is the drill stem. All right. The drill stem is hollow. All right. Steel here. And you're going to watch it. And this is basically just a glorified jackhammer. All right. That's really heavy. So you'll watch how it works here. Okay, so many of you, most of you, maybe all of you haven't drilled a lot, but that is flying. He just went down a foot in 15 seconds. All right. He is really, the geoprobe is moving. Now this looks like soft soil and flatland. So, you know, like when we drill with a geoprobe in gravel bars in Western Montana, we don't go that fast. But one of the primary advantages of geoprobes is how fast you can advance. Now, one of the things we talked about with the wireline was the cuttings that we brought to the surface were just those fine, like slurries. So one of the things you can do with geoprobes is you can core. And let me draw how this works. So in a geoprobe, all right, so we got our ground surface here. Now at the tip, we have that metal casing, right, that you see sticking out. And at the tip of that, there's two ways we can drive a geoprobe, but most of the time we've just got a drive point. All right, it just comes down to this circular drive point. And so when we hammer on our drill stem, we're just shouldering away all the sediment and rocks around this drive drive point and driving our stem down. All right. So when we core with a geoprobe, there's a portion of this drive stem that we can pull out. And then we pull that out, and then we're going to drive an inner casing down through that hole. And this inner casing is going to be hollow, and it's going to collect soil inside it. We'll drive that down about, you'll see it's about 1 meter, this inner casing, and it'll collect about 1 meter of soil. And then we pull that back up, we reinsert the triangle, and when we drive down this opened hole, so then we would drive down to here. And then we'll pull this section back out, advance our core tube, and then do the whole operation again. So that's what you're going to see him do here. He'll be pulling out the inner triangle, then he'll advance the core tube, then he'll put the inner triangle back in, drill this whole thing back down, and then advance the core tube again. The advantage there is we're getting discrete, intact cores of our material. All right, so that's invaluable. We can use that to test hydraulic conductivity, to just log the formation and the type of materials we're in and the depths, and map out the subsurface. So he's pulled out that inner triangle. Now he's going to put this core tube on there. Now he's going to drive the core tube.
How are you? Oh, my blood sugar is 175 this morning. Ready.
All right, so he's removed the core. All right, this tube now, that tube holds intact core of our substrate. All right. And then he's going to put the metal point back on and re-advance casing. So he's got to put another section of casing on. So this is a lot of drilling, is taking a section of drill stem, you put the new section on, you drill down, then you load another section of drill stem. And drillers get really good at this, putting sections of drill stem together and taking them back apart again. Look how fast he's going. Man, that is soft stuff, let me tell you. All right. So GeoProbe, if you go into environmental work, you're going to work a lot with GeoProbe. That's just by far the most common method for shallow investigations. And the reason why is you saw how fast it can advance in a perfect world. But these things are also, they're not huge. They're pretty cheap. They're track mounted, so they can get a lot of places. Or like mine sits in the back of a pickup truck, you know, so it can be driven around. So there are a lot of advantages to the GeoProbe. So for the GeoProbe, the way we case is that, like I was talking about before, with we take, so here's our drill stem. We're going to take, these drill stems are designed so that you can fit a, say, a 1-inch or 2-inch PVC piece of pipe down inside your drill stem. So you put your casing in here. This is going to be, say, 2-inch PVC casing. And you might have it screened over, say, this interval. And then you just pull the drill stem up, and this guy stays down in the hole. All right. And so the bottom of your hole is still your drive point, and you just pull your casing out. Or sorry, your drill stem. And then the material collapses in on your casing. Okay, so that's GeoProbe. Now we're gonna talk about rotary drilling, and rotary is the most common and most used drilling type. And there's a whole bunch of different rotary types and ways of drilling rotary. You can, with rotary, we can core, and we can just run a essentially a chipping bit. Coring is much slower, and the regular bit is much faster. And it just depends on sort of what we want out of our hole, whether we need to characterize and get core, or whether we're okay with just hauling ass and not using the coring bit. So this rotary movie is from the oil patch, but all these techniques are the exact same that we use in groundwater. What? My video is unavailable? They took it down. We'll just use this one. Hopefully it'll be good.
You've got something up your sleeve.
What you didn't know was you were surprising your father.
Not many people know how wells and water systems work. So let's take a look at the key parts that make up a typical home water system. First is the well itself, a shaft or deep hole in the ground extending down into the water-bearing formations. The average well is about 200 feet deep, and most are drilled by specialized drilling equipment. Casing must always be placed in the top part of the drilled hole to prevent the risk of surface water getting into the well. In some types of rock formations, casing may extend much deeper to prevent the hole from caving in. Some wells use a well screen to let water in and to keep sand out of the well. A pump is needed to get water out of the well and into the home. Water from the aquifer is pumped from the well into a pressurized tank, which stores water for use when the pump is not running. From this distribution point, water is piped to individual use points in the home. The planning, design, and construction of a water well and home water system needs to take account of geology and environmental conditions at the building site. The first step is proper planning. How much water is required to meet the needs of expected water usage in the home and garden? Where should the well be drilled? What well yield will we get? What water system equipment may be needed to provide a reliable supply? The builder or homeowner should get expert advice about the availability and reliability of local groundwater and the safest place for drilling before the first dirt is disturbed. This is the time most prospective well owners turn to experts. The drilling contractor will have current information on any state and local environmental restrictions and permits required for drilling, as well as mandatory construction standards for water wells. The driller can recommend the best place for a well based on the character of the soil and bedrock and the required distance from other structures or possible sources of contamination. A water well contractor with extensive experience in the area will have records of previously drilled wells. These records provide helpful information on the location, depth, and typical water yields from nearby wells. In low-yielding rock formations, a well probably will need to be several hundreds of feet deep in order to provide adequate supply. But a well yielding as little as a half-gallon a minute can still provide 700 gallons a day, more than enough for a family's needs. Homeowners need to know the capacity of their well. Virtually all wells will provide enough water for in-house needs, but not all wells can support garden and lawn irrigation systems. Back in the early days of rural and contractors use accepted well construction methods to ensure that the well is safe from any surface contamination risks and will give the best yield available from the formations. Several techniques.
Okay, so this is a rotary bit right here, and you see we call this a tri-cone bit. So each one of these burly things here is a roller cone that has these little protrusions, and those are diamond encrusted carbide steel, and these things roll as the bit spins, and they just pulverize and break up rock. Another important part of this system is that you have to circulate a fluid to bring the chips back up to the surface. So that the drilling stem is hollow, and we use 3 different fluids to bring chips, so all the rock that's broken up by this thing, back to the surface. The first is air. We just use compressed air and blow the chips back up the hole into the surface. The second is water. We use just water that we pump. And the third is called drilling mud. And drilling mud is essentially bentonite mixed with water. And then we might add other elements to that drilling mud. If we're in a place where we might hit artesian conditions, we'll add barite, and that makes the density of the mud really, really high, so that even if we have really high water pressure, it won't push the mud back up the hole. So when that process of pushing the well, or pushing, if you get enough water or oil or gas coming back into the hole at high pressure, you can push your drill stem out of the hole, and that's really dangerous. So we can weight the mud up with barite and other material.
Are used to drill water wells. The most common is the rotary drilling method. Other methods are cable tool, jetting, and driven well points. In rotary drilling, a drill bit is attached to a string of drill pipe. As the drill string is rotated, the bit acts as a grinding machine. Cuttings are flushed upward and out of the hole by circulating a special drilling fluid called drilling mud down through the drill pipe and back to the surface.
Okay, so drilling mud is just one. I would say probably most water wells are drilled anymore with air, but you can use air, water, or mud.
This drilling fluid also serves to cool and lubricate the drill bit, and by stabilizing the wall of the hole, it can prevent possible cave-in before the casing is fitted into the hole. In areas of hard rocks, many drillers prefer to use a rig that operates by compressed air to operate a downhole air hammer to break up the hard rocks. The compressed air also blows the crushed rock fragments to the surface and any water that flows into the well during drilling. Another drilling technique uses a pounder machine, usually.
All right, so so the main thing with the rotary is that spinning action. Now here is some video of them completing the well and filling the annulus with grout. This is an important part of the process.
Well construction standards. Diameter of the drilled hole is usually an inch or two wider than the diameter of the casing. The space between the drilled hole and the casing has to be filled to prevent surface water from migrating downward along the outside of the casing and contaminating the aquifer. This filling is called grout, and it may be either cement or a special clay called bentonite. Sometimes most of the space is filled with fine rock pieces from drilling, and then the top 20 feet is grouted with cement or bentonite. If the well is drilled into rocks that are crumbly or into sands and gravels, a well screen probably will be needed. The well screen is a sieve or strainer-like cylinder attached to the bottom of the casing. It allows water to flow into the well while preventing fine rock particles or sand from entering. Well screens are not all the same, and the well driller will select the opening size of the screen depending on the size of the rock fragments or sand that make up the aquifer. With the casing and well screen or other intake in place, a flushing or backwashing of the well may be performed to eliminate.
Okay, so this is another process. Once we install a well, we will pump water in at really high pressure or pull it out as fast as we can. And that's called well development. And the idea is just to get clays and drilling mud pumped out and pushed away from our screen. All right, so developing a well, you just pump it really hard or inject, and you're just trying to wash out as much of this clay from the drilling process as possible.
Fragments and stabilize the area immediately adjacent to the well intake. This is called developing the well.
Okay, so let me see if there's anything else I want to. All right, so rotary, we can also, let me see if I can get a rotary core. The idea with a core, with a core, I'm not seeing the one I used to watch, which is too bad. And I don't want to randomly click on YouTube videos. But so the idea with the core is it's with core drilling is it's a rotary method. And so we've got our hole here, and we're drilling. And our core bit has these shoes at the base here. And these are my diamond shoes at the base of my core of my drill stem. And then it's got another tube inside. That sits right in here. And so this thing spins. All right. These diamond shoes cut down. And as they do that, we leave behind this column of rock that comes up into our core tube, all right, and fills our core tube. All right, and then on the downside, you know, we're still cutting here. So here's the outside of our hole. And now this core tube is hooked up to the surface via a wire line. And what we do, we drill down. Usually these are 1 to 2 meters. If you're drilling on a big rig, they're 5 meters. All right, and you drill down, you collect core for anywhere from 1 to 5 meters until you fill this core tube. And then you stop drilling and you pull up on the wire line. It's got some special teeth down here that hook on to the bottom of the core. They break this column off and you pull it up and you've got a core tube sitting at the surface, just like in the GEO probe. You got this tube and it's got your core in it. You send another one of those tubes down in, it hooks in, and you start drilling again. All right, so you advance about 1 to 3 meters at a time. And then you pull core. And then you advance again. Now, when I am drilling rotary, I have to circulate fluid so the water can flow around the core tube and out and back up. So it brings up mud, but I'm collecting core. This is the most expensive. Drilling method. All right, it requires this wire line, is a lot of working parts. You advance slowly when you're coring, but the benefit is you get intact core and you can pull this out and you can do all kinds of stuff with it. So you can log it, you can you can run tests on it. You can analyze it. It's perfect core for doing hydraulic conductivity measurements. So this is like the gold standard. And if you had all the budget in the world and you were doing scientific investigation holes, then you would only do core. If you're just trying to get water, you never do core. All right, it's the worst idea. So it's really a scientific and characterization method that we employ when we really want to know exactly what's going on in the rock at a given point. Now, the nice thing with rotary drilling is I can switch. So I can drill with a tricone until I get to my depth of interest. I can trip out, I can pull off the tricone bit, I can put on a wireline coring bit, and I can go back down and I could core over the next 100 feet if that's what I'm interested in. And then I can trip back out, put another tricone on, go another 200 feet, and then core again. And so a lot of, especially oil companies or science boreholes, will core only over given intervals of interest and then drill with a tricone the rest of the time. Okay, so this is just a little trip into drilling. It is a huge and complicated endeavor. So I have a friend of mine who his whole consulting business is in well design, completion, and drilling methodology. So that's what he does. I thought I'd give you guys a couple examples of, in the last 10 minutes, of projects that I've worked on where we had to think a lot about drilling and well design. So the first project was a project in Australia. And we were investigating this huge regional groundwater system called the Great Artesian Basin. The aquifer is recharged way up in the northeastern tip of Australia, in the tropics. And then this groundwater system flows underneath the whole interior of Australia, which is a big desert. And it's a large artesian confined aquifer. So you've got this thick sequence of clays above the aquifer. And this shale is called the Bulldog Shale. And this is the Great Artesian Basin, the GAB. And our science question was this. The GAB kind of ends out in the desert in South Australia, and nobody knows really where the water's going. There are a few springs. So you'll be out in the middle of the outback in this huge desert. All right, you haven't seen water for 3 days drive, and then you'll see these large springs and oases out in the desert, and they're fed by the GAB, but they account for, like, we think something like 1% of the GAB discharge. And so our science question, what we were there to investigate, was how much is just leaking up through this aquifer and then being evapotranspirated at the surface. And even though you can't see any visual evidence of discharge, how much could be leaking up through the aquitard. So what we did is come in. So this, in our research area, the depth of this is about 300 meters. Okay, so a little less than 1,000 feet. So what we did in the GAB is we wanted to, so this is shale, really low conductivity. So if we drilled a hole, which we did, so we went in and we're going to drill a hole. All right. Oh, and this is highly artesian. So the wells in this area that drilled through the GAB and were finished into the GAB, the head is 10 meters above land surface. All right, so 30 feet is how high the water stands above the land surface if you complete a well down in the Great Artesian Basin. So they're really, really artesian. All right, but this Bulldog Shale is so low hydraulic conductivity that even though this Bulldog Shale is fully saturated, if we were just to complete this well and not let it intersect with the GAB, all right, we made some calculations. It would take 1,000 years to fill our borehole. It's just so low conductivity that the water leakage out of the hole or out of the shale into the hole, it would take 1,000 years to fill it up. So what we wanted to do, well, we wanted to apply Darcy's law. We wanted to figure out what the pressure profile across our Bulldog Shale was, but we needed to do that without getting down to the GAB. And so we cored this entire length. We rotary core. The entire length until we think something like 10 meters between these two boundaries. So we think we finished it at about 10 meters. Now let me tell you, it's dicey because we don't know exactly where the boundary here is. And the last few drilling sessions, so we were drilling 24 hours a day for like 2 weeks on this project, pulling core, logging core, sampling it. When we got to about 260 meters, we were starting to get pretty scared because if we intersected the GAB, then we're going to have great artesian water just rushing out our borehole, and we would have lost, we wouldn't have been able to do anything we wanted to do. So it was pretty scary. So then what we did is we strung pressure transducers. We tripped out of the hole. We strung a series of pressure transducers. So this gives me head. And then we grouted in the entire borehole. So we filled the entire borehole with grout. The reason why we grouted this whole thing in is now, first of all, grout hydraulic conductivity is way higher than the clay. So bend your mind around that. Cement has a lot higher hydraulic conductivity than clay. All right. This was like a high K zone for us. And now, instead of having to fill the whole open annulus of this borehole, I've only got to fill the porosity. And in fact, the porosity of the grout is already full of water. So I only have to pressurize the water. So we brought our response time from 1,000 years to about 1 month. So after about a month, my pressure transducers are recording the pressure in the fluid just outside the clay. And the reason why is because we grouted it in. All right. And we only had to transmit the pressure pulse through the porosity in our grout. All right. We also then had a complete log of intact shale from the surface down to the base. So we could sample that shale for various chemical constituents. And we wrote all kinds of papers on the isotope composition and various chemical composition of the pore waters in those shales. And it turns out that a lot of this water in here is like over 1 million years old, and it records all kinds of cool changes in the groundwater flow system from the Great Artesian Basin. And then we were also then able to calculate how fast water had to be moving up through the system from the pore water chemistry changes. Right, so that was an example of us having to design a drilling technique and a completion technique for our science problem. And we spent probably 3 months just in design of the well and the completion. Another project I worked on, well, we'll get into that on Tuesday, but we also designed a borehole to store nuclear waste in at 5 kilometers depth. And so drilling to 5 kilometers is you're pushing drilling technology to the max. And there's a lot of, like, the completion and the drilling methods, we had to spend a lot of time thinking about what can be done in terms of drilling. So I'll just talk real briefly about that on Tuesday. And then we'll talk about, finally, what we're going to move into now is once we have this hole in the ground and it's screened, how do we use these wells to tell us things like the hydraulic conductivity, the storativity, and aquifer characteristics, aquifer configurations. How do we use these drill holes to understand what the subsurface looks like? So that's what we're going to get into on Tuesday. All right, so we're out of time for today. I got a request to post the video links. I'll put those up on Moodle after class. Any other questions before we go?
Will you have your office hours? Oh, sorry.
No, go ahead.
All right. Well, will you have your office hours?
I will have office hours, yes.
Okay.
I got a question about screened wells. So are the bottom of the casing still open to the wellbore?
It totally depends. They're not always. Sometimes they're sealed, and sometimes they're not. Usually,
Okay.
Usually they're sealed. What usually, like for a water supply well, what you end up doing is there may be 3 or 4 sections that supplied enough water. So you might screen in 3 or 4 places, and then the bottom of the hole will still be closed. So,
Okay.
So yeah, it can be either, but generally they're closed, and it's not always that you just have one screened location.
Right. So I guess for wells that are like used for, I guess, like tracer tests and everything, like, are those wells like open? Because generally you want to just sample to that depth, yeah?
Yeah, so if you want, so really important point is when we sample groundwater or measure the water table depth, it's really important to think about what the screened interval is. So if we want really discrete samples, let's say I want to know exactly what the water chemistry is at this depth, or the water table height is at this depth, then I want a short screen that's closed on either ends right around that area.
Right. Okay.
If so this would be generally science wells, and we tend to call anything with a short screen piezometer. So these short screened wells are piezometers. Most scientific wells are piezometers. Most water supply wells, we usually have long screens because we're trying to maximize how much water we're getting.
Okay. Yeah, thank you.
Sir.
Yep.
I how I know that you're going to need information so that you know where to put the screens. Do you do testing drills? I mean, you do, most likely you're going to do some desktop investigation first, but do you also do like maybe two wells? One is a test well, and then the other one you set it up for the screen?
In general, we're not going to have the luxury of having two wells. And so we characterize as we go. So we can look at various things, and we'll talk about this more on Monday, but what do we do with the borehole? But as we pump or as we drill, we're constantly recirculating fluid down into our system. And if I hit an area that's yielding a lot of water, I'll see that. I'll see a lot of water coming in, and I know that'll be a good spot. And if I'm just trying to get water production, what the drillers do is they'll have a rough idea of where water usually is. They'll drill to that depth, and then we pump for a while and see how much yield we get. And if we don't get very much, then we'll drill some more.
Okay.
So we kind of characterize as we go. If you're coring, you look at the core. So that's what a lot of oil and gas exploration, they're pulling out cores or analyzing the mud, and they call it shows. So you're looking for shows of oil and gas in your core or in your mud. And similarly in water, we can pull core, like we're doing a bunch of drilling up in bedrock in the mountains, and we want to have screens where there's fractures. So we'll look at the cores, figure out where there's fractures, and then say, okay, we want to screen over this interval. So you kind of characterize as you go. That's the most common.
Do they use any like foam drilling muds? I know in the oil industry that has been a thing, but I don't know if I know those can be like highly designed.
Yeah, I mean, basically any drilling that you do in the oil industry can be used for water. It's generally, we don't need to.
Right.
But yeah, the mud design and engineering can get very complicated. And in the oil patch, they go for it. Often, you're generally thinking about how much lubrication do you need, and then how much weight. Because if you're entering pressurized reservoirs, say like the Great Artesian Basin or a pressurized oil or gas reservoir, you need to make sure that you're not going to rocket your stem back out the hole. So a lot of it is weighting the mud up.
So how common is that? The rock shooting your tube back out of the...
It's not, if you're doing your homework and being careful, it's not too common, but it happens, and it's dangerous as hell. I mean, when we drilled this hole, I can tell you everybody was pretty nervous. I was sitting on the hole, for our last 10 meters, and me and my friend were the ones trying to make the call when we were going to stop. We wanted to go as close as we could to the boundary, and it was scary. I mean, we were all, the closest data we had was like 10 kilometers away on the bottom of the boundary, and so we didn't know where the bottom is. So yeah, it's, you know, had we pushed it another 10 meters, maybe we would have had problems. We had our mud weighted up, but you know, you also don't know what exactly the pressure is. So, you know, it's not real common, but shit happens.
I can just see it now. Monty Python. Oh.
All righty. Well, I'm gonna I can either stay here for office hours. I need to stop recording though. I think I'm still recording.